The next part of thermochem that I want to talk about is about enthalpy and how we communicate this new word enthalpy. Now, enthalpy has an H in it, and so I don't know if that's why they decided to give the symbol for enthalpy an H, but that's what they did. Delta obviously meaning change. It is an energy, it is a potential energy, and therefore, like all energies, they are measured in joules, kilojoules, gigajoules, megajoules. The most common is going to be your kilojoules for reactions. If it has a little naught there, that's saying SATP. SATP meaning standard ambient temperature and pressure. So this means it's 25 degrees Celsius. 1 mole per liter solution, and at 100 kilopascals of energy. Those are in your data booklet, so you don't actually have to memorize 100 kilopascals of, I think I said energy, pressure, 100 kilopascals of pressure, 25 degrees Celsius. You don't have to memorize that, it's in there. But understand that this means that it's at SATP. And obviously, if I'm combusting something, it's going to get probably hotter than 25 degrees Celsius. So these numbers can be different than our actual raw data that we're doing in the lab, simply because my room is not going to be 100 kilopascals of pressure perfectly or 25 degrees Celsius perfectly. But in order for me to be a scientist that puts something into a data booklet or into a published article, I'm going to have to control those variables. Okay, so that's a discrepancy between the perfect data and your experimental data. One difference is going to be this SATP. The other thing that they'll give is little subscripts are for a reaction. Maybe it's a single replacement, maybe it's a redox reaction, which we'll get to in another unit, but any kind of reaction. If it's specifically a formation reaction, element plus element yielding the compound, then we'll put a little F here. If it's specifically the decomposition reaction, and by this I mean your compound going into its elements, so the exact reverse of each other, then we're going to put a little D here for decomp. And you often see a little C for combustion because we often are talking about the combustion reaction here. Okay, so because all of these are reactions, then this is the energy here is potential energy. It's the potential to react, the energy that's given out in the bonds breaking, bonds forming. So that's what delta H is. It's about potential energy. Q equals MC delta T was kinetic energy, and enthalpy is potential energy. And of course, the reaction can warm up the surroundings or cool down the surroundings, and therefore we have a transfer of energy. Energy cannot be created or destroyed, but rather just change from one form to another. That would be your first law of thermodynamics, right? So what we're doing is we're pausing our conversation about MC delta T and looking at the potential energy part. The junior high will have hopefully solidified that endothermic and exothermic are words that we use for reactions. If it is endothermic, it's because the temperature goes down, it gets colder. And an example of this would be like maybe those emergency ice packs that you put on your knee in a game. You pull it out of the first aid kit, you break the two compounds. There's it's like an egg kind of inside. There's a yolk and then the rest of the white. And so when you're doing this with it, when you're massaging the package, what you're doing is you're trying to crack that inner circle so that it mixes with the outer circle. And as those two chemicals start to mix, the inner circle and the outer circle, as those two chemicals start to mix, they react. And their reaction gets cold. Therefore, it's an endothermic reaction. That reaction getting cold because what the system is doing, those reactants, they are pulling in energy into their breaking and forming of bonds. Okay, their overall, the breaking and the forming overall ends up being energy in. And we're going to talk more about that part that I just said, breaking, forming, etc. later. So hold on to that thought, but we're going to expand on that. But the reaction is gaining energy overall. Therefore, if I'm pulling the energy into the ice pack, your knee is going to feel that energy leaving, and that feels cold to the knee. So the energy is going into the chemicals in the package over here, and so the knee feels cold because it feels the energy leaving to get to the package. So all of that was sort of a junior high understanding of what enthalpy is. And so, endothermic is said by the word endothermic, by the fact that it's getting colder and feels cold, or the fact that my temperature change goes down. And maybe that the system gains energy. Here is how we're going to say endothermic in Chem 30. I'm actually not going to jump out and say this is endothermic or I touch the test tube and it feels cold. Maybe, but probably not. Probably this is how we're communicating it. The first way we're going to communicate it is I'm going to have a delta H and I'm going to put a plus sign, a positive sign in front of the number. So maybe I'll tell you, hey, for this reaction, which is a combustion reaction, let's say, oh, actually that's impossible. It's a formation reaction. For this reaction, it equals 100 kilojoules of energy. And I'm going to put a plus there to say, I mean endothermic. Okay, so this isn't a plus as in a number line. This is a plus as in endothermic. I'm saying the word endothermic by putting a plus sign. Chemists love to do that. We love to create a symbol to represent a whole reaction or idea, not reaction, word, pardon me, idea, paragraph. And so here we have a symbol of a plus, but really what I'm shouting is endothermic. How else we might say endothermic? The second way we're going to communicate endothermic is it's a reactant. So I'm going to have chemical A in my ice pack and chemical B in my ice pack, and 100 kilojoules of energy go into the reaction as well, and they're going to make product C. So this here is going to show me that, oh, I see energy on the left-hand side of that arrow. That means it's endothermic. And the third way is an energy level diagram. In an energy level diagram, you have the y-axis being your delta H or potential energy, because it's the same thing. And on the x-axis, it's progress. I kind of mean time, but also this is all happening in an instant. And so I can't really say like 1 second, 2 seconds, 3 second kind of time. And so I just have this progress as the reaction progresses. So my reactants are going to become products, okay? And those reactants are going to gain energy. In fact, here they gain 100 joules of energy, kilojoules, pardon me. So the distance here should be 100 kilojoules over there. And so I have 100 kilojoules that those reactants are going to gain before they become their product C. If it's a specific reaction, you're going to talk about specific reactants and specific products. So nitrogen and oxygen become nitrogen dioxide is my product. You actually write those on there. Okay, but if I see this staircase go up, right, this shelf goes up from the second shelf, that's how I know it's endothermic, because the shelf went up. If it's exothermic, it's the exact opposite. So the junior high part is that the system or the reactants lose energy. And here you can see on this energy level diagram, that third way of saying it, the reactants do indeed lose energy in order to become their products, right? And so this energy then ends up being a drop down. The surroundings get hot, the temperature goes up, my delta H is negative. So once again, I'm going to put that in this formation reaction, my delta H is negative, and let's make a different number here. So let's say negative 50 kilojoules. And so I'm going to write it as a product because we're producing that energy. And so I would have A and B give me C and 50 kilojoules of energy. I would write there. And then the energy level diagram is the same. Y-axis, x-axis, reactants, products. We have an arrowhead at the end. This arrowhead represents this arrow, right? So it's just one arrowhead. And that the numbers here, or maybe sometimes I just put delta H equals 50, but of course I have to put a negative 50 and units, kilojoules, because it is losing that energy. So the diploma, the unit test, the workbook is not going to say exothermic. It's going to say negative product. Here's my shelves, and we go down from my product to my reactant. Okay, so communicating enthalpy is hidden into those three terms. We're going to try two reactions here that practice all three of those ways. Now, something I didn't finish saying is that those ways are called delta H notation, a enthalpy reaction, and then of course I did say the potential energy level diagram. So we're going to practice all three of those ways. So let's say they ask you to indicate the formation reaction and they want it to be delta H notation. If it's delta H notation, then what I'm going to do is I'm going to put reaction like normal, and then space, delta H equals. So formation of water, the reaction is going to be, maybe I'll pick a different color because I don't love that color there. Hey, let's pick red. For delta H notation, a formation reaction is going to be hydrogen, which is diatomic, oxygen, which is diatomic, making H2O gas. Now, I want a 1 in front of this because when I look up what the delta H is for this, right, looking this up in the data booklet on page 4 and 5, we have a whole list of formation reactions. And so the delta H for this is going to be in my data booklet. I'm going to need to look it up. And it's going to tell me that it is negative 241.8 kilojoules. Is that right? Yeah, kilojoules. And the title of that says kilojoules per mole. So always look at the column title. That guides you a lot. First of all, it tells you its formation. Second of all, it tells you that it's kilojoules per mole. So 1 mole of water vapor. So, and by the way, this table on page 4 and 5, I can only use it for formation reactions or decomposition reactions. As soon as it's combustion or something weird, I'm going to have to use a different method. I cannot use the number straight out of here. But here we're talking about formation, so I can use the data booklet about formation. So my formation reaction is this. The negative here, so first of all, I have written it in delta H notation, check mark. Second of all, the fact that that says negative means it's exothermic. So as soon as I see this, I know that this reaction is exothermic because of that negative. So let's say they wanted it not in delta H notation, but they wanted a thermochem reaction. So that's where I'm going to put the energy into the whole thing. So here I know it's exothermic. Exothermic means energy is produced or given out overall. And so I have my oh, I forgot to balance the reaction. I'm sorry. I had to do this whole thing. If this is a mole, 1 mole, I need 1 of my water. Therefore, I want to keep this balanced with a 1 here. And therefore, 2 hydrogens, no problem. But I want to put a 1/2 oxygen here. Because 1/2 times 2 is 1, I have 1 oxygen here, therefore I have 1 oxygen here. Remember, oxygen looks like that when it's O2, so if I just had half of that, I just have 1 O, so 1 O, 1 O, so that makes sense, okay? So in thermochem, it's a really good idea to balance with fractions, because I have to put a 1 here, therefore I have to balance with fractions there. It's not as important in the other units, but it is really important here because the number I look up is for 1 mole of water, so I need a 1 there. Okay, I've said that lots now. Okay, so that's really important. So anyway, back to the thermochem reaction. I have hydrogen and I have half of an oxygen, just like I had before. And I still have 1 H2O gas, just like I had before. But this being negative means exothermic. Exothermic means the energy is produced. And so it's a product. Now remember, these are a list of reactants and they create a list of products. So therefore it is plus because it's produced. I don't keep that negative in there. I do keep a unit though, kilojoules per mole. So I know it's not gigajoules or megajoules or something like that. So that is communicating it in as a thermochem reaction. And so the third way then is an enthalpy level diagram. In the enthalpy level diagram, a reminder that what we have is our energy level diagram, enthalpy level diagram, same thing, that this y-axis is delta H or its potential energy, and this is progress, and I always have 2 shelves. So, and my reactants and products. This is specific, so I'm going to write specific things on these lines. And those specific things are the reactants on the top shelf, the products on the bottom shelf. The staircase goes down because it's exothermic and because the energy was released. And how much energy was released is negative 241.8 kilojoules. So all of this goes on to my specific enthalpy level diagram. Let's have a look at an exothermic reaction. So here or an endothermic, pardon me, we just did exo. Here I have decomposition of glucose. So when I'm doing my delta H notation, I'm going to take my glucose and make it go into its elements, decomp. Carbon is a solid at room temperature or at 25 degrees Celsius. We have H is a diatomic and it's a gas. Oxygen is diatomic and it's a gas, balanced with a 1 in front of that glucose. Where am I going to find this delta H? When I look at my data booklet, which is full of formations, I remember that this is a formation reaction if it was flipped. So if it is flipped, I can then just switch the sign, okay? Flippy, flippy, switchy, switchy. So if in my data booklet it tells me the formation of glucose is negative 1273.3, then the decomposition is going to be positive 1273. So in my delta H rotation, I'm like, okay, this is a decomp where I'm going into my elements. And therefore, my delta H for the decomp is going to be positive 1273.3 kilojoules per mole. And so delta H notation is the reaction space, delta H equals positive number because it is endothermic. Now, because it's endothermic, and I know that from the positive, when I'm writing my thermal reaction, I'm going to put the energy as a reactant. And so here I have my glucose, and that much energy is going to produce those chemicals. If it's an enthalpy level diagram, you have to be specific because it's a specific question, so you have to give a specific answer. I still have my axes labeled the normal way. My glucose is now my reactant. These elements are my product. It's balanced. You can see the reaction, but my energy is going to go up because I've inputted 1,273.3 kilojoules into these chemicals as I'm breaking and forming bonds. And so this is going to then have an uphill shelf that looks like that. Okay, so 3 ways of communicating enthalpy. They take a bit of practice to know which one you're supposed to communicate and to be able to look up those numbers and flip them for the decomp.